that, I'll let Andrew take over, and thanks
Sure.
so much for coming.
Thank you.
Let's welcome our speaker.
Great, thanks. So, yeah, my name's Andrew Rosenberg. As you know, this work was done mostly, I'll say, by Adam Goodkind and David Guy-Brazan. They're both in the audience, so if I make mistakes, I'm sure they won't hesitate to point them out. But yeah, this will be a relatively high-level look at typing and what we can do with it. So first, just like as a illumination of the title of the talk, it comes from a time when electronic communication was telegraph and largely Morse code. And so this notion of the fist of the sender was, a reference to the fist that a skilled telegraph operator would make when using the machine. So just any sort of clarification about where like this fist notion comes from, it's from this. The terminology and technique of the fist of the sender came from a recognition that skilled radio listeners and radio operators could recognize who was communicating via Morse code by the individual operator's patterns. That they would be transmitting the same sequences of dots and dashes, but you could recognize, oh, this is operator X, or this is the same person I heard last week. This ended up being useful during World War II as a root of military intelligence, where if someone listening to a radio signal could recognize that an operator was moving from position to position, that would track with, say, troop movements, things like that. It's not only a sort of military intelligence situation. There's a fictionalized story of two people falling in love with a corresponding telegraph operator based only on kind of what they say and how they do it. So I try to sort of balance kind of the humanistic elements and the sort of intelligence security kind of things, but yeah. So this is sort of where we were in the, up to say like the mid to late 40s. Now our communication looks like this. The message I want to communicate is it's not that different, right? We still have this notion of rhythm in terms of the keys we press. We still hold each of these keys for differing amounts of times. We have different intervals between the keys we press. So in some ways, the space has gotten much richer, right? We don't have one signal that we're saying on, off. Instead, we have about 98 keys, plus or minus, based on your keyboard. But the techniques developed in, or at least human techniques developed in and around World War II, still have merit now. So I'm going to take a step back a second and ask the question how we type. What happens when we sit down to construct language and communicate it via our hands through a keyboard? And we've got a number of steps that we go through that are all sort of these cognitive intelligent things, right? We start out with some sort of conceptualization of what we want to say and why, right? The impact of language and the structure of language on this remains sort of a controversial topic. Is all of our thought mediated by language or not? That's not something I'm going to get into here, but there is sort of this sort of primary step of I've made a decision to communicate something, I want to get something across. Then you've got another step going down around sentence planning. You have some sort of semantics and syntax interface where you're starting to put together elements of a sequence of words. You then retrieve those words. Again, the hard lines between these three sections are false. There's gross interfaces between here. And then finally, once we have a sequence of words, or at least a partial sequence of words that we would like to type, we then come down and we get into the mechanics where we start sending this information down to our hands and into the keyboard. The thing I want to stress in this is that each one of these processes, heavily interacting processes, are unique to who we are, both in how we think and then in some cases our physiology, right? The length of my fingers, the speed at which I type, the familiarity I have with different words through muscle memories, starting down at the mechanics of this, are all fairly unique to me. And then as we move up, we're all sort of very comfortable with the idea with how I think defines who I am, right? And these two are sort of one and the same. So if I can get the question then I want to pursue as we go through this is, if we watch someone typing, what's revealed about the individual? And there's a limit, obviously. It's not everything. But I'm going to start with some examples, which are just recordings of me typing. So this is what it looks like when I type my name. Right? This is going to repeat. This is what it looks like when I type a name that's not mine, but sort of similar. So this is just live typing. One of the things I noticed in the second one is I'm actually pretty good at typing the Andrew part of Julie Andrews, but I've got this weird pause right before the S because it's very rare that I do that, right? So the question is, can you recognize, one question is there something about how I type things, particularly familiar terms, that can say, yes, you're telling the truth, yes, you're who you say you are, or no, you're not. Like, all things said, when Julie Andrews types Julie Andrews, she probably types it much more fluently than I do. And if somebody else comes in and types Andrew Rosenberg, they probably don't type it with the same rhythm that I do, right? And then, just to push this one step further, we're going to talk a lot about authentication and identity as kind of a core kind of exercise here. But there's this other question of just what else is revealed. And we've got processes that are communicated both by the things we say explicitly, right? My name is Andrew Rosenberg, my name is Julie Andrews, et cetera, right? And then there are things that we sort of imply, right, that aren't said explicitly, that you're never going to get by sort of a formal syntactic and semantic analysis, that you need either some level of pragmatics, some level of paralinguistics, or maybe looking at kind of the rhythm and pace at which people type, right? Maybe that's communicating some element of it. And it certainly is in speech, right? A lot of my other sort of parallel and tangential work is on intonation in speech, and so that's a little bit of the scientific perspective I'm bringing to this. Okay, so we've got three major research threads sort of around this idea of let's look at people's typing behavior. And the first is authentication. Is our typing unique? When I sit down at a computer and I start typing, does it work like a fingerprint? Where a fingerprint is a very high level, or does it work much worse, more like a password or something? Then we've got a question of demography. Right? Maybe it's not true that there's a uniqueness to how I type. Maybe it's not me alone, but maybe I type like people who I'm similar to. Maybe, for example, all people who grew up in New York type similarly. Maybe all people of the same age type similarly. Maybe people who work at computers for, say, 12 to 16 hours a day type similarly, right? Or maybe not. Maybe this is all just nonsense and we'll investigate it and then walk away. It's science, right? I mean, that's always a possibility. Right, okay. So then this third question is just process, right? So we started this work in this sort of very application-centric view. Like, we want to be able to confirm who someone is, who they say they are. We want to generalize to start to say, can we assign this person to a group of people? And then we said, okay, well, let's also look at what typing can reveal about cognitive and mechanical processes that may be going on during typing. Right? And to see if there's any insight that we can take from there to sort of share more broadly about sort of language and this sort of special sort of case of it. Okay. So we'll start with authentication. And I'm going to just dispel any notions, right? Is our typing unique to who we are? And the answer is no, not exactly. It's not as reliable as a fingerprint. It's not going to replace a retinal scan, but it's pretty good. And I hope by the end of today you'll believe that it's a useful vector for security and a potential risk vector for privacy, right? And these two are always the same. And if I've communicated that, then good enough, right? So the question is then, right, if our typing is unique to who we are, or at least partially unique to who we are, what does that mean? And the upside of it, right, if just having access to how I type allows somebody to pretend to be me, there's a lot more ways to breach security. And just to make clear that this isn't total science fiction, Coursera started doing this. Coursera has their verified certificate, whatever, you are who you say you are, and now you know all there is to know about whatever class you took on Coursera, and you pay some amount of money to say, like, yes, it's you. So they've started putting together this two-track identity confirmation bit. The bit on the right is turn on your webcam, take a picture of yourself during login, and then when you sign up to enroll for your certificate, you take another picture and you confirm it's yourself. That's pretty secure, unless you were to say, hold up a picture of someone. right? Which is not that hard, right? And that's fine, right? It's pretty good. But so they also have this second bit here. And they're not totally candid that they're tracking typing. It's just you have to type this phrase, right? But it's very clear to me that, you know, if it was just like I can copy and paste this phrase, that's useless security. Like, it's useful, and there's a lot of sort of behavioral science which suggests that having somebody sign and write out an honor code does actually promote good behavior. I don't think that's what they're doing. I'm pretty sure they're tracking how I type this phrase, this stock phrase, looking at the rhythms of my typing. Okay. Yeah, there was an animation that I didn't use. Anyway, now, in this security space, the first thing I'd like to communicate, and this is sort of a very strong second takeaway message, is that passwords are bad. Passwords are not a good security solution. And I have a couple of kind of infographics which hope to convince you of that. High password complexity is great, but it can make it really hard to crack, right? So you've got this thing, right? As your password complexity goes down, it gets easier to crack your password, and vice versa. The downside is the probability that you will write it down goes with this as well. And as soon as you write your password down, it's no longer secure, right? The whole notion of it is it's something that you have to remember, right? And if you don't, then you've ruined it, right? So as soon as you write it down, your password lacks everything, right? So then there's this other question of, okay, every application, every password I need should be unique, right? I should never be repeating a password, right? So that also inversely correlates with, am I going to write it down, right? I can probably get away with a pretty complicated password, right, if I use it for every application I log into, right? But if everyone needs to be unique and they have to be complex, the likelihood of me writing something down reaches 1. And then there's sort of another approach where people are like, no, no, I don't write it down. I aggregate my passwords, right? And this can be, oh, if I forget a password, I'll just have it sent to my Gmail password, right? Or whatever your favorite email carrier of choice. Or I'm going to use Max Keychain, or I'm going to use 1Pass, or any of these things. And again, password repetition, the more this happens, the more likelihood that you're going to have a single point of failure somewhere in here. So, passwords, great in spirit. We all understand how they work. But as a practical security solution in a relatively adversarial context, they're not particularly great, right? So the question then becomes, what else do we have? And a number of things that people have looked at. The most reliable that people seem to have come around to is a hardware-based solution, something in the physical world. And one area of this that people have used are these sort of two-stage passwords, right? Where you have essentially two chunks of hardware which have to be in concert with each other. It's your phone, it's a mobile device, it's a pager once, whatever it is, which is going to say, I'm going to try to log in, now I'm going to send you a password to another bit of hardware, and you can't get on unless you have both of these, okay? This is, you know, very much akin to the, you know, safe deposit box two-stage hardware solution of the past. Other things that folks have been looking at are biometric security approaches. And these include things like fingerprint scanners, retinal scanners, and in this work, the way we type as a biometric. Okay. Another issue with passwords and the login style of authentication is that users get authenticated very, very rarely, right? You'll get to your computer in the morning, you'll log in. That's one login. You'll sit at your desk for, say, 4 hours. If you're very responsible, and I'm sure all of you have taken some sort of class in sort of light security, every time you stand up and leave your desk, you should log out, right? Most people don't, but that's, you know, at least the theory of it. So in practice, you'll probably be logged in, say, you know, twice every 8 to 10 hours, right? Maybe less, maybe more. That's pretty rare considering how much open space that means your computer is just available. That can actually be much less if you have any sort of secure system and persistent login from machine to machine beyond even what's going on at a terminal. Anyway, so the goal of continuous authentication or active authentication is to make sure that somebody is who they say they are based on their behavior intermittently, at regular intervals throughout their regular use of a machine. And then the idea is, if there's something suspicious going on, elevate security, right? And this can mean reprompt for a password, move back to some other two-stage authentication, consult a second party, say like, hey, manager, does this person have access to this? Or in an extreme case, brick the hardware, right? Start a fire in the computer, like destroy everything kind of thing. That's obviously extreme, but so we do this work and we give these presentations. So just this comes at the end, which is stupid. This work is funded by DARPA, and so the folks who are in the room are sometimes military folks, and they're like, if a phone that they've deployed somewhere is actually compromised, they want that solution. They want that physical, not lock the person out, but like lock the person out, break the machine, totally wipe the hardware. Like they want that as a, anyway, so it's not something I made up, but it is obviously a very extreme case. Anyway, okay, so what we're saying, this is sort of the view of continuous authentication writ large. What we're looking at is define something suspicious as a user not typing the way he or she usually types, right? And this can mean both different key frequencies, different typings, different text, right? You've never written to your mother before, and now all of a sudden you're writing to your mother. That's going to be suspicious. You probably have a problem, right? And then, so the claim here is that like typing is now a biometric. It's something that we have inherent in who we are, in our physicality, and our mental processes, which is relatively unique to who we are and unique enough to indicate if something suspicious is going on. Okay? So that's where we are. So now let's talk about how we measure this. And there's a long history of work in keystroke dynamics. Almost none of what I'm going to say for the next like 3 or 4 slides is stuff that we developed. The idea here is you have a series of keys. We have about 98 keys in general on a keyboard. This is just 3 of them. Essentially, what you're going to say is at one particular time, you get a key press signal. The key is depressed for some period of time, and then it's released. This overlap of a T and H here is incredibly common. When we type, it's very rare that you click a key, lift one up, click another key, lift one up. This is one of these things that as soon as you think about it for, I would say, a beat, or if you're at a computer and you try to do it, you will be like, oh yeah, of course, I've never typed in this like one key and then another kind of way. So the 2 measures that folks look at most consistently and have been shown to be useful kind of for 30 years, 30 or 40 years, are measures of a key hold and measure of a key interval. And a key hold is this, key press to key release. Right? How long do you hold down the T button when you type a T? How long do you hold down an H button, et cetera? And second, key intervals. What's the timing between a T and an H? And what's the timing between an H and an E? And with these 2 things, you get a lot of mileage in terms of understanding how someone types. The one thing that I'll kind of point out is that when you just watch, for example, like the videos of me typing my name and stuff, you only get key presses there, right? So you can get the interval timing, but you have no insight there to how long my fingers have lingered on these keys. So there is something sort of a level kind of beyond just what's observable. Oh, anyway, okay, so I did have this. Okay, so how can you measure these things, right? For a study and a data collection like we did, we said, hey, undergraduate research volunteer, like come sit down at this machine. We're going to track your keystrokes. And then they sit on custom software, which they know is logging their keystrokes. Okay, so in general, on a local machine, you need that kind of local software access, right? In a perfect world, in a perfectly secure, undetectable world, again, sort of putting the kind of government spook hat on, you want kind of kernel level access to the timing of these things for those who know what that means. On the other hand, it's really easy to get key down, key up signals through any web browser with a little bit of JavaScript and jQuery, right? So the notion that this is hard to do should be dispelled, right? As apps and services and our interaction with the world moves away from software on a physical machine, more into software as a service type remote access things, the notion that you can track or it can be tracked should become more and more obvious, right? Your typing behavior is not as simple as like what goes into a text box necessarily. In addition to that, Google Docs and other collaborative editing tools will send each key down event. And each is sort of not true because they'll batch a bunch of them up and send them on in a packet to make things simple. But there's a lot of information being sent. OK. The good news, right? So that's the bad news, right? It's pretty easy to track this stuff, which on one hand means it's really easy for systems to implement this security, which is potentially great for you if you trust those systems. On the other hand, it's pretty easy for someone to pick up your typing behavior in any sort of like malicious setting. So now the good news is spoofing keystrokes is hard for a human to do, right? I can't, even looking at someone typing for a long time, having access to their information, it's really hard to sit down and type like someone else. So kind of know that. OK. So that's one direction of tools that we look at. Another is stylometry. And stylometry is investigation of linguistic qualities, style, which identify who an author is. And this is work that's generally done on static text, so finished, complete products, usually books. It was famously used to identify authors of the Federalist Papers and of Primary Colors, and infamously used to incorrectly attribute work to Shakespeare, right? So it's not perfect. We're all very comfortable with that. Don Foster is less comfortable with that, but it's OK. His career is fine. Was better. Anyway, and essentially the idea is we're going to try to say what words you use, what kind of syntactic structures do you use, what are your linguistic tics that make you sound like you when you type. Okay? And similar techniques have used throughout natural language processing and related to our work on demographics, they've been used in things like personal attribute recognition, recognizing things like do male and female writers write differently, which is a mildly, to put it mildly, controversial idea. Does age impact our language use? Yes, it does. Does political orientation? To a lesser extent, yes, et cetera. OK. So how do we measure style when we talk about text? And this is an incomplete list. People are very creative in their techniques to do this. But there are things like just statistics of word use, right? Do I write the word of a lot? Do I write the word Andrew a lot? Do I write you know a lot? I don't. But one thing that I do when writing academic papers is I'll use the phrase in order to way too often when to will suffice. So I'll say like, in order to discover this, rather than to discover this. And that's one of, I'm sure, myriad things that I don't know about my own writing. But statistics like that are indicative of who we are. There are kind of linguistic tics. You can then move into a little bit of syntax and say, oh, does this person use a lot of adverbs? Do they use a bunch of modal verbs? How do they use different punctuation? Do they capitalize a lot? Do they really like em-dashes? Some people do. Some people will never use an em-dash. Lexical diversity, right? Is this person a relatively sophisticated writer, varying the kinds of words they use a lot, or are they very repetitive and very clear, right? And this is another signal that people use. They've used lexical diversity and lexical density and also like readability measures. So like how difficult is this in assessing kind of grade level appropriateness. And things like sentence length. So these are relatively easy to extract from fixed text. The more text you have, the more reliable they are an indicator of who someone is. And the work we're doing doesn't use a whole lot of text. So they're useful, but it's not really quite enough. And then one of the things that we did introduce when looking at this work is an intersection of keystroke dynamics and stylometry. And again, some of these have been done before, some of them not. And here we want to say, well, let's look at the length of pauses, how much you wait before and after a different part of speech category. So how much do you pause before a noun? How much do you pause after a determiner and things like this? Similarly, around punctuation. Are you one of these people who you finish a sentence and then you wait for a little bit and then hit a period? Or do you hit a period at the end of a sentence and then wait before you start another one? How do you behave when you misspell a word? How long a typing burst do you have? People will typically, and there's good cognitive reasons to do this, they'll plan essentially a block of text, type it all out, and then wait. And then type out another block of text and wait. The length of that burst and the behavior on either side of it is pretty indicative of your proficiency, whether you're a native speaker, and to some degree, some of the other things that we look at here. And then also, and we'll talk about this quite a bit more later, different revision measures. So how often do you revise your text? And when you do, how much do you end up deleting? So these are the three different types of things that we measure in terms of authentication and other kind of demographic indicators about typing. Now I'll do kind of the boring slide, which says this is the data we're working with. It's one of these necessary things. It's about 1,000 Louisiana Tech students. They both sat down. In both of these sessions, they participated in a very similar task. In session 1, there were about 800 people. About 500 came back the next time. 500 or so did both of them. It's great. Okay. They self-reported their demographics, so we know they're liars. Okay. And one of the ways we know they're liars is the handedness question, right? Does anybody know roughly how many people are left-handed in the world as a percentage? Okay, it's about 10%. Okay. Does anybody know how many people are ambidextrous in the world? Like legitimately like have no preference? It's like, it's vanishingly small. It's way less than 1%. Okay. Our group, roughly 10 to 11% of people said they're ambidextrous. Okay? So we know most of them are wrong, or North Louisiana is a very weird place. It's always possible. Okay, so, and then some people just didn't respond, and that's okay too. So we have gender, handedness, native language, typing style, which we haven't investigated as much as we should, and then computer usage as a proxy for how familiar they are with using a machine. Okay. So they sit down, they respond to a series of 12 prompts. Important here, the prompts used in session 1 and session 2 are totally distinct. So in all our studies, the training material we use and the test material we use will be from responses to different questions. So we're not just learning, oh, this person's responding to a movie question and then we know everything about movies or anything else like that. We make sure that they all type at least 300 characters. In practice, they typed a lot more. We get about 900 or so keystroke events, about 400 or so characters, roughly 80 words. And this is the amount of material we're using most of the time unless it's said otherwise. And we have this time resolution, which won't impact anything in the future, but it's thorough. Okay, so how do we do authentication? There's a little bit of machine learning. It's fairly simple. In the space of machine learning, if you've never seen machine learning, I don't want you to feel dumb by not understanding this. Anyway, the idea is we're going to learn a template for each user based on mean and standard deviation measures for each type of keystroke dynamic measure, right? And we'll define different groups of keystroke dynamic measures, but essentially it would be like, how long does this person hold a D down? Okay, well, we've seen 5 of them. Here's the mean, here's the standard deviation. We'll remember that about D. We'll do the same thing for all the other keys. We'll also do what's the interval between each of these. Okay, we have 98. 98 times 98 is about 9,000-ish. That's how many features we'll have there. Okay? We'll use a distance measure comparing a test sample when somebody comes in and delivers a bunch of keystroke information compared to some template. And the way we do this is a measure called a scaled Manhattan distance, where we take just the absolute difference of each of the features independently. V is this test vector, and the mu is the mean value of that. So you would say, okay, well, this person now held a D down for 10 milliseconds. Can't do that, but 10 milliseconds. The mean was 15, so the difference is 5. And then we're going to divide that by that user's standard deviation. It's just a way of saying how far apart these two are. And then you say the person that we verify the test vector to be, it corresponds to that template. Okay? And we have 3 different measures about how we do this. There's the number of imposters incorrectly allowed into a system, the number of true users incorrectly rejected, and then the equal error rate, which is the point at which these are equal. Okay. So let me just quickly run through how good some of these measures are. And we'll start with one that's pretty bad. This is just looking at key intervals. So the time between key press and key press. One of the problems here is that the space of 9,600 features is very sparse. But what this means is 1 out of 3 times we're going to make a mistake. Either we're going to kick you out of your own system or we're going to let someone in. And this is based on watching someone type for about 60 seconds. Okay? Then we come in and we say, okay, well, maybe the full space is a disaster. Let's just look at alphabetic characters, A to Z. And A to Z does quite a bit better. Now we're down to like 1 in 5 mistakes. Okay? Then we come in and we say, maybe we want to know start and end of words. So we throw a couple back in. And we say, okay, spaces, commas, periods, apostrophes, that's all important, and they can stay. And again, this is, now we're down into keyholds. I'm sorry for the typo on the label there. But anyway, these are key holds. This is so how long does someone hold a D down? How long does someone hold an E down? And this is all of a sudden now we're in the space of a usable statistic, right? So the lingering time, much more valuable than the key interval time, but we're not quite done. If we come in and we say, only look at these extended digraphs, intervals between keys that don't involve spaces, right? They can have a word ending space, but nothing at the beginning of a word, okay? That's valuable. And what is this telling us? So just to like demystify just a bunch of numbers on the page, what we start with here in the terrible area is let's just look at the intervals between all the keys. Okay, so there's way too many of them. And then we say, no, let's start to focus in on words. And something about linguistic context now matters, right? If we know that we're dealing with a single word at a time, that's really valuable. And what we learn in the next two bullets is understanding what happens when someone comes into a word is incredibly variable. But what happens when someone comes out of a word is now pretty predictive. So how long do you wait between hitting a space when you're finished a word? That's generally considered like to be part of that word, you finishing it. But the amount of time between you hit that space character and you go into the next one, too variable to be useful. Okay? So that's where we're at down here. Okay, and then we have one extra thing, which is this digraph hold, where we're summing two consecutive key hold times. And we see that the performance there is about 40% better or so than looking at individual hold times. Okay, what does that mean? It should be if the amount of time I linger on each key is completely independent from one another. We should get no benefit here, right? Because we've only made things a little bit harder. We've expanded the feature space. But what that means is the timing of these two key holds are incredibly interdependent. They're really correlated, and modeling them together makes it better. So this is still more evidence that we have that the context of in which you're typing, the words you're typing, the phrasing, something about that does filter down into this low-level mechanic in a way that is individuating for us and identifying. So this idea of looking at the interdependency of these keystroke measures, which really sort of just started out as a lark, it was like, oh, let's see what happens, indicates this idea that kind of predictability matters. And we have this property that there is a correlation between these keystroke measures and how predictable the next key is. When we talk about predictability, we're like, well, okay, you type TH, what's the likelihood that you have an E? Well, it's pretty high. What's the probability that you have a space? Pretty high. What's the likelihood that you have a Q? Pretty low. If you see THQ, right, chances are the timing information either on the interval and the hold on that Q is going to be longer, okay, because it's somehow unpredictable. So what we do here is now, rather than taking just the actual times, we say, well, what's the time subtracting out what we think to be the expected time for this keystroke for you? Okay, so if we eliminate that, we get not a huge gain, but a 3 to 5 or a 3.5 and 2.2 reduction of error in a couple of these things. So it's not huge, but it does still count. Another thing we looked at, which folks have looked at in a variety of different ways, is lexical context. And here the notion is the TH that we type in the is different from the TH that we type in breadth, right? And we can know that, right, because we have access to broader lexical context. So we're going to represent new features based on the TH in the TH in breadth, and just general THs. We can also say, well, maybe we want to get a little bit more broad and say it's not just the word that you're saying, but also its syntactic category. So let's look and see if THs in determiners are different than THs in adjectives, et cetera, et cetera. And then we'll make this a little bit broader, and we'll look at function, content, and then these top 20 function words, these Pennebaker words. It turns out, and this is a slightly different configuration of the experiment, so our digraph hold measure is a little bit higher than it was before, at about 8%. When we introduce this function content distinction, this is the notion of saying, are you saying then, the, therefore, or are you saying thistle, throw, verbs and nouns, essentially. Okay? And doing that gives us an extra 3 or so % reduction of error. So again, this matters. Lightly, but it matters. Okay, so this work that we did sort of took this notion of keystroke dynamics and said, you know what, we need a lot more context. One of the different directions that this work has taken that others haven't necessarily, and a lot of the work that I talked about as being ongoing for the last 30 or 40 years, a lot of that work is on fixed text. Things like the Coursera Honor Code, things like when you type your password, let's make sure that you know it, that you have your rhythm, right? Which is great. I mean, and they strengthen passwords a lot, and it's really good. What we've done is moved in the direction, and again, we're not alone in this, but it's a smaller group of people who look at free text, just like start typing. Okay? So the things that show up here now are predictability, the use of linguistic context, and this idea of using these n-graph hold times, so you sum of consecutive sequences. The bottom one in particular is incredibly simple. Everything should be using it, and it probably will soon enough. Okay, so we move to these other questions. Can we do things like recognize demography? Is there any signal which says men and women either type differently in terms of their mechanics, in terms of their style, or in terms of an intersection there? We look at gender. We look at handedness, left-handed versus right-hand. We omit our self-reported ambidextrous people because we know they're liars. And native language. Or is your native language English versus anything else? We have richer sort of responses to the anything else category, but we don't have enough people to like reliably model like the 10 or so Chinese speakers, right? Okay, so the sources of similarities which might happen here is the question of, are there sentence planning and lexical preferences that are indicative of these different groups? There is some light correlation in terms of men and women. I don't think there's anything in the literature about left-handed versus right-handed people really thinking differently, though people will make claims about like right brain dominant, left brain dominant. I'm very skeptical of that as it relates to sentence planning and these lexical preferences. But where it does matter is in the mechanics, where you have things around dominant hand, are you faster with your left hand, faster with your right hand, et cetera. The mechanical thing could potentially impact gender, where male hands are generally a little bit larger than female hands. I'm not really convinced of it, but it's possible. Okay, so how do we do this? So we construct distinct groups of subjects drawn from session 1 and session 2. No subject overlap, no prompt overlap. So totally unique groups of people. We're going to try to model these different demographic groups by keystroke dynamics, stylometric, and production features. And we'll just explore a bunch of classifiers because we don't really care about the classification routine that goes into this. We're just looking to see if there's any signal here at this point. And we measure this by F measure because we have in each of these tasks a pretty strong minority class. Less strong for gender, where it's 47-53 or so. But for handedness, we're 90% right-handed, 10% left-handed. For native language, like 83-16 or so. We couldn't really find particularly good differences between gender, right? A little bit of a signal, nothing really that significant. You can move the line, but it's not a big deal. Where we do see big gains is in recognizing handedness, where again, you can't do it very reliably, but if you take as the idea that only 1 in 10 people are left-handed, we can actually find twice as many than you could just by guessing, and then still more of that for recognizing people who do not have a native language of English. And there you have things like lexical choice, revisions, and also typing bursts. They tend to make shorter like spurts of typing. Okay. So now we then say, we have this assumption here. Cognitive and mechanical processes impact our typing. That seems like a pretty sturdy assumption. So the question is, can we learn anything about cognitive and mechanical processes that go into this by examining typing behavior? And the 3 things we'll look at here are task recognition. Can you determine what kind of mental task, what sort of cognitive demand a person is experiencing by looking at their typing? And then let's look at what happens when people type multi-word expressions, and let's see what happens when they make different kinds of revision and see if we can learn anything about their cognitive and mental processes. So one thing I didn't tell you about the prompts when I described them for authentication is that they fell into these 6 categories to try to get people to engage in different behaviors. And this is a taxonomy of cognitive tasks. It's, it exists in the world, but it's not perfect. This notion of a level and increasing complexity is contentious, let's say. The lowest level cognitive task you could do is just remembering something, right? Tell me about, the most recent movie you've seen, books you've read, what were they about, et cetera. Moving up to increased sort of cognitive demand of understanding things, applying, analyze, and eventually creating things. Okay. So, again, now we're going to look at multi-word expressions. For those of you who aren't familiar with them, multi-word expressions are lexical constructs of multiple words that in many ways behave like a single unit. Okay? These are things like compound nouns, compound verbs, idioms, proper names. Essentially, the definition behind this is that the meaning, the correct interpretation of these expressions is roughly non-compositional or idiosyncratic, right? You don't know what San Francisco is because you understand what San is and Francisco is, right? They work as a unit, right? Similarly, traffic light and post office, you can sort of like parse it out, but really that's just one thing, right? If somebody was like, oh, we're going to talk about like a gridlock light as opposed to a traffic light, you don't really know what that is, right? You can sort of fuss it around, but like there is a single referent to traffic light, which is very clear. Okay. So there's a theory here which suggests that lexical retrieval, the process where I decide what word to use, might behave as a single unit, where when I try to type traffic light, I don't say it's traffic and then it's light, but rather it's just one thing. And then when I type it, I should type it as a single unit. And it should behave more like one word than two words, maybe. Okay, and then there's another claim here around our lexicon, which suggests that we might have, just to understand like how big an issue this is, or a linguistic phenomenon it is, that we have as many multi-word expressions in our lexicon, in our vocabulary, as we do single words, that they're just everywhere. Okay, so we said, all right, well, let's look at pause times between words that are within a multi-word expression and outside of a multi-word expression, and somewhat confirming this single retrieval hypothesis, our pause times are much, much, much shorter when we're talking about multi-word expressions than not. So this is interesting in its own right. And then for applications, we have this notion of, okay, well, maybe we should be treating these expressions differently. Because when we talked about that, we had this notion that we have to treat end-of-word characters as kind of special. And maybe in these contexts, we don't. Another thing we looked at is, okay, so we know that multi-word expressions are always faster, almost always faster in the main. Does the relative quickness of getting at a multi-word expression versus a regular pair of words, does that differ based on the type of behavior the person is engaged in? And surprisingly, the answer was yes, right? So there's something about the other cognitive processes that a person's engaged in which seems to be having an impact on this lexical retrieval, and particularly lexical retrieval of these pairs of words as they relate. I don't think we have a perfectly clear story about what's going on here, particularly why the categories are sort of all over the place. We're not seeing a very obvious trend here. It could just be that the categories are bunk, right? That they're different, but there's not an ordering that is claimed by the literature here. But the point is there is something different, and we are getting a clear kind of cognitive intersection between these retrieval times and typing times and the different tasks that people are engaged in. Okay. So the third thing we looked at is typing errors. And some of the sources of typing errors are things like memory, right? What was that word again? I don't know. Factual mistakes. You type something, I'm going to be giving this talk on Thursday. Just kidding, it's Friday, right? Things happen. Sentence planning. I make choices in structure, make choices in word choice. Maybe I change my mind halfway through I'm putting a sentence together. Lexical retrieval is this notion of maybe I typed the wrong word, maybe I skipped a word. Mechanical errors like these fat finger errors where you either miss or type 2 characters instead of 1. Coordination errors between your 2 hands, things like TEH. Right, so we've got a lot of these different sources. One question is, how many of these things are individual to who I am? Right? Are my errors similar to my errors and dissimilar to yours? Is that more or less informative to who I am? So just for context of what we're doing, we're going to talk about revisions in typing using phrasing that comes from disfluencies in speech, where we have a referendum, which is the deleted text. Here are these 3 keystrokes corresponding to WED. Then we have a number of delete characters, which clear out that WED, and then type Monday, and that's going to be the repair. We're going to measure a few different things here: the percent of deleted characters in an answer, the rate of revisions overall, the length of the referendum, the mean and standard deviation, and then comparison of the text between the two. Right? And what this analysis, particularly the comparison of text, allows us to do is look at different types of errors to see if people are more or less likely to make different mistakes. So you have things like a transposition mistake where inquired is spelled IU instead of UI. Fat finger mistakes are where you're off on the keyboard by about one position. So you type AGTER and then you have to go back and make after. This doubling thing is kind of interesting because it implies something about how we duplicate characters. That this happens a lot means there's essentially a marker which is, hey, double it, which can detach from the right character. That it's not necessarily double L, but somehow the character to type and the hey, double it signal are pretty tightly correlated, but can get out of sync. And if they get out of sync, you get these errors like SMAALER instead of et cetera. Early finger errors are when you eventually need to type this character and you put it in too early. We have full replaced words where somebody types a word, deletes the whole thing, types it again, and then types a new word. A surprising percentage of mistakes are unchanged, where you type a word, then you delete it, and then you type it again. You essentially revise your revision. You thought you had to delete it, and then you don't. This is very incomplete in terms of our taxonomy of errors. We don't have a way of dealing with, say, other misspellings. And part of this is just the reality that often the information we have is incredibly incomplete, right? If I type DI, delete I, and then write describe, what kind of mistake is this? Well, I don't really know. Like, there's just not enough information in those two characters to say either I've completely rethought the word, I've made some misspelling, who knows, right? And that happens an awful lot. So about half of the mistakes we have are uncategorized. Okay, so here's one of these things we've just sort of begun to investigate. And in this very simple way, we said, let's look at revision rate and revision length. And we're going to compare across these demographic and task categories and see if there's anything to this, right? Do native or non-native people make more revisions, or do they make longer or shorter revisions? And here we found no significant differences. And then we said gender. Okay, men or women, do men make longer revisions, shorter revisions, et cetera? No, they don't. Handedness is a little weird. There's no real good reason to think that, like, you know, people who are left-handed should make mistakes more than right-handed people, and, you know, good, they don't. And then typing proficiency, right? I sit down and I type all day, every day. You type an hour a day, right? Do we make revisions differently? No, we don't. In terms of like how frequently we make revisions and how long the revisions are, totally the same. And we're like, okay, fine, task, right? We know that people are doing these different things. The creative thing, maybe they want to revise things a little bit more, whereas just remembering a book, you don't really make as many mistakes. No, still nothing. There are no differences in terms of revision rate and revision length in any of these things. So, fair enough. So then we said, okay, well, does analysis of revisions and taking like the revision context contribute to authentication at all? Like, doesn't help with any of the demographic stuff. And here, one of the things we look at is this question of, when I make a mistake, is that kind of like my true typing identity? And then when I revise, I get a little bit more careful, and then I'm like, oh, okay, now I got to get this right. And that's sort of an artificial version. Or when I make a mistake, is it because I'm not like myself? That I've made some sort of like hiccup, either cognitively or physically, and then don't trust it. It's not like who you are, and then look at the next one. And so what we did is we omitted keystrokes associated with either deleted text. We also tried omitting ones associated with the repaired text, et cetera. And ignoring the reparanda from analysis helps. So essentially what that's saying, and it helps by about 10%, and this is more than most of the other errors or improvements that we found on these sort of marginal gains by looking at context. So essentially what this is saying is when you make a typing mistake, you're not typing like yourself. This is a distraction. And it could be because the fat finger issue, right? If you transpose a key, all of our statistics about that key are totally bunk, right? Because you meant to be typing a D and you type an E or something, right? So this is still pretty interesting, and we're still working on how we can incorporate this most robustly into these authentication approaches. So there's something to revisions. Anyway. Okay. Quick summary. We looked at typing for these three kind of directions, right? Authentication, typing does make up a fairly reliable biometric. The more material you have, the better it gets. It has really broad security and privacy implications because it's so easy to collect and so easy to implement some of these behaviors. The latency on them is incredibly small. For demographics, some demographic indicators are revealed, but not with a whole lot of reliability, right? Men don't always type like men. Left-handed people don't always type like left-handed people, et cetera. Where we do see a little bit of something is in recognizing if somebody's a native speaker, which is somewhat understandable, right? We've got a long history of stylometry in this space. And then for process, in some ways typing can illuminate some things around the cognitive and mechanical processes that go into typing. And I think this is still a kind of interesting area within cognitive science and sort of an intersection of technology and cognitive science that's worth continuing to investigate. So what are some, like, it's not science unless you say that you're not done. So what are some of these open challenges, right? Mobile is, changing everything. This is sort of a broader question of device changes, right? Do I type the same on different keyboards? And the answer is, probably not. But the question is, how can you adapt in a reliable way to deal with that? Temporal changes. Does a person change over time, and more specifically, how, right? If I type before coffee, I type differently, right? If I injure my hand, clearly I type differently. What about when I get better at using the language? For those of you who are programmers, people have looked at stylometry within programming. You recognize that you can type particular programming constructs much faster the more you use them. How does this impact this as a useful technology? And then beyond that, how much can you infer about specific speaker states? Can you pick up emotion? Can you pick up things like sleepiness and intoxication? Google, at least for a minute, experimented with the idea that you could have it warn if you're sending email beyond a certain point of night. So like if it's 2 to 6 in the morning, you'll get like a little notice to say like, do you really want to send that email? Which is like a really simple technology here. But you could imagine it being a little bit more sophisticated, right? Where if you're like really angry, say, right, maybe don't send that mail. Like maybe you want for yourself just to be like, maybe cool off, reread it, make sure that's what you want to say. Or like maybe you're obviously drunk and you can't really type, but you've managed to put something together, and like maybe don't email your boss. And then this is all sort of self-protective. And then there's this other question of, can you pick up, and there's a good amount of work in the speech community on recognizing, and then also on text analysis, in recognizing early and unobtrusively neurodegenerative and aging effects, right? There's a really incredible longitudinal study of looking at nuns' diary writings as part of their tradition, kept copious diaries. And some of them developed Alzheimer's, some of them didn't. But looking at their writing allowed researchers to look back at their writing in their 20s to be like, oh, what's going to happen to these people? And they found some really remarkable effects of being able to, with some reliability, predict this thing. So the notion of, can I tell that somebody is, say, like about to have a stroke, maybe not about to, but maybe, in the world of, is this going to be a problem? I think there's potentially interesting research to go in that direction. Okay, so that's my pitch. Thank you. This is how to find me if you're interested. A special thanks to Adam and David, who really did all this work, and then special, but less, to our broader collaborators who we worked on with this project. The folks at Louisiana Tech collected all the data, and they're awesome, and have done great work in this space. Regardless, the folks at NYIT do great work in security, and Aaron's just a rock star. And then, again, a special thanks to the folks who pay for this work. A couple of active authentication PMs. Many of you probably know Angelos. He was at Columbia in computer science for a long time. He's on leave, and I guess on loan to DARPA for the next couple of years, but also really good. And that's it.